Today, we're going to start a new topic that is an application of centroids, also a good practice with distributed loading as well. And the topic is called fluid statics or hydrostatic force. The idea here is that if I have an object, if my object is submerged under a liquid or under a fluid, they're going to experience pressure. And a fluid can mean either a liquid or a gas. We're going to talk today mainly about pressure caused by liquids, but we also experience the same concept with the pressure caused by the air surrounding us. As you go up to higher elevations, the air pressure decreases, which is why in an airplane flying at 30 or 40,000 feet of altitude, you're going to need to have additional pressurization to be able to have enough oxygen to breathe. So pressure definitely changes with altitude. In air, it also does in liquids like water. So what we're going to use is the fact that the pressure varies linearly with depth. We'll think of it as depth below the surface of the liquid. And I want you to keep in mind that pressure always pushes inward on the object, whatever the surface is, and it is always perpendicular to the surface. That's enough words. Let's actually draw a picture for what I'm talking about. So here is the surface of our water. And underneath it, we have submerged an object. Let me do the simplest object I can think of to draw, which is just a cube or crate, some kind of a box of material. And so the idea is that if I go down a fixed depth, there will be a certain amount of pressure. And so if I want to look at just the top surface of my box, since it's horizontal, the whole surface is the same depth Z down below the surface, maybe call it Z1. Which means that entire surface is going to have the same exact pressure acting on it, and it's going to be perpendicular to the surface, pushing inward on the surface. So that might be how I would draw the pressure on that top surface. It's going to be a uniform pressure, and depending on how deep below the surface it is, determines how big that uniform pressure is going to be. Let's do the other horizontal face. So what if we go to the bottom of the box? It's a farther down below the top. So we might need to go down a different distance, Z2. And if we do that, we're going to get another pressure on the bottom. It's also going to push perpendicular to the surface and inward. So my arrows this time are going to be going upward. There's the pressure on the bottom, and it's going to be a bigger pressure. So this is also a uniform pressure. The reason it's uniform is because that entire surface is the same depth below the surface of the water, but it's going to be larger in magnitude because it's deeper. And this is what gives us kind of the idea of buoyancy. You've probably heard of buoyancy before. You have the concept that if you put a really dense material into water, it sinks. If it's a fairly low density material, say styrofoam, it's going to float. And it has to do with the fact that there is a difference in pressure on the top versus the bottom. So you've got a bigger force pushing up than pushing down. But if I were to draw a free body diagram of this, I've also got the weight of the material pushing down. So depending on how big the weight is compared to this pressure differential determines whether it floats or sinks. Let's look at the sides. The sides are a little bit more interesting. Well, if I look at this left side over here at the top, we're going to have a pressure that pushes. Again, it's always perpendicular surface pushing inward. At the bottom, we're at a deeper depth though, so it's going to be a bigger, and that pressure is going to vary linearly with depth. So that means my pressure is going to have this kind of a shape to it. And kind of fill in on the side to let you know that it is three-dimensional. So we'll have pressure at the top, pressure at the bottom that are different. So from a side view, this is going to look like a trapezoidal loading. What about the other side? It's going to look exactly the opposite. Big pressure on the bottom, smaller one at the top, linear variation. So on the sides, we're going to get a pressure that I drew in green that increases with depth. Okay, I didn't draw the pressure on the front face or the back face, but the same thing would happen on the front face. The front face would look just like one of these side faces. You'll have a pressure that's smaller at the top, bigger at the bottom, and it varies linearly. And I'm just not going to draw it only for the fact that it gets really crowded and complicated if I draw all 6 sides on here. So we'll just draw those 4 sides, gives you an idea of the difference between the pressure on a horizontal versus a vertical face. It'll look a little different. So let's actually quantify how big that pressure is going to be on those different surfaces. The equation that I like to start out with is pressure is going to be defined by something we call a Greek letter rho, G, and then Z. Need to define a couple of things. So this is the pressure caused by the fluid. Rho is the density of the fluid, and the units of that we're going to use are kilograms per cubic meter. G is the acceleration due to gravity, which in SI units is 9.81 meters per second squared on Earth. And then Z is the depth below the surface. And I should mention, up here at the surface, we have atmospheric pressure on top. But we are in this class going to neglect atmospheric pressure. Z is the distance below the surface. Let's check out the units. The density is kilograms per cubic meter. G is meters per second squared. And then Z is meters. And you will hopefully remember that a kilogram meters per second squared, that is a Newton. That's a force unit. So what's going to happen with my units is I end up with a Newton per cubic meter times a meter. I get newtons per square meter. And if you're not familiar with that in SI units, that is called a Pascal, which we use a capital P lowercase a to mean a Pascal. Now, a Pascal is a teeny tiny amount of pressure. So don't be surprised if the pressures you find from our submerged objects are kilopascals or even megapascals. So pascals times 10 to the third or 10 to the sixth. We're going to get really big pressures because a Pascal is a tiny unit of pressure and we're dealing with big things submerged deeply underwater. That is what we're going to do when we're dealing with SI units, where we have density in kilograms per cubic meter. I actually want you to think of the equation slightly differently when we're dealing with English or US customary system of units. Here's how it's going to be different. Typically with US customary system, we are not provided with density. Instead, even if you go and look up on the internet, what's the density of steel in English units, it might call it density, but what it's really giving you is something called specific weight. So the equation is going to look like this. Pressure is this thing that we're going to use a Greek letter gamma for times Z. P is still pressure. Z is still depth below, but what gamma is it's called specific weight. It is not density. It has the same function in here as the product of rho and G. Because whereas rho density was mass per volume, then you multiply by G to get over here force or weight per volume. Specific weight just skips that step and it's immediately either pounds per cubic inch, or in our book, it's more likely going to be pounds per cubic foot because we're dealing with big distances. So that's the specific weight of our fluid. And since it's already in force over volume, we don't need to multiply by G. We just multiply by the depth to get the pressure. So our units in this case are going to look like this. We start with specific weight, which is in pounds per cubic foot, and then we multiply it by Z, which will be in feet. And we simplify and we get pounds per square foot. That is pressure units. Force over area is a pressure unit. So when you are doing these, I want you to write down all of your units in every step and cancel them out. That's going to help you remember to include G over here, because if you end up with kilograms at the end, kilograms is not force. You shouldn't have kilograms in your pressure when you're done. So if you're left with kilograms, you know you forgot to multiply by G. Same thing with here. If you start with pound, pounds are force. So you don't need to multiply by G because you're already in force over area kind of units for your pressure. Let's go look at how this applies to some actual problems. I want to start with analyzing the pressure on a horizontal plate. We got a surface level of water somewhere, and we go down some depth below it to a horizontal plate. So we're looking below the surface, a depth Z. And because that horizontal plate is all at the same depth, we are going to have the same pressure everywhere on our surface. And let's figure out how big that pressure is. So the pressure, the equation that we just said, comes in two forms. It's either P equals rho GZ or P equals gamma Z. And it just depends on what units you're working with. So those units are going to be either newtons per square meter or pounds per square foot. All we need to know now is what is the fluid made out of, what's its density or specific weight, and how deep is it? And we can calculate a pressure value. Now, we don't usually like drawing the picture like this because this is three-dimensional and you've got to put some perspective in there and it can get a little confusing. So we very often do a 2D simplification so that we can treat this as a distributed load, which lets us use the same techniques we used earlier in the semester. So let's draw a 2D version of the same exact picture. There it is, two-dimensional, and here we have a downward distributed load, which I'm going to call W. Remember how pressure is P? Distributed loads we used W for earlier in the semester. I know some other textbooks use Q. We're using W for distributed load. So if I want to figure out how big the distributed load is, well, do you remember what kind of units distributed loads had? It was force over length. We wanted to know how much force we had over a certain amount of length in this direction. So instead of newtons per square meter, I need to have newtons per meter or pounds per foot. So that means I got to take this pressure and multiply it by basically how far into the page did it act. We're going to use the letter B for this dimension. And the reason we're using the letter B is because our textbook uses the letter B. But if you want to think of it as the breadth into the page, that's totally fine. I don't like to use the word depth because we oftentimes are thinking of depth as how deep is it. I guess you could use width, but I don't want to use W because I'm already using W for distributed load. So the book uses B. I think the best word, if you like to have something with a mnemonic device to help you remember it, would be B for breadth. But it's the into the page distance. So if you know that into the page distance, then you can now calculate distributed load is going to be pressure, which is rho gz, times B. Or in your other units, it would be gamma z times B. And that's it. And now what are the units going to be? They're going to be newtons per meter or pounds per foot. Those are going to be our units once we've converted our pressure to a distributed load. The last thing we're going to do is take that distributed loading and replace it with an equivalent force. So you guys remember how to do that, right? We take the area under the curve and then we put the force, guess where? Right in the centroid of that area. So if it's a rectangle, it goes right in the middle. Now to do that, I need to find that area. So my equivalent force, which we're going to call F is going to be the area under the curve. So the height was W and the length here, I didn't ever put on my diagram. Why don't we call that length L? So since this is a rectangular distributed load, F is going to act in the middle at L over 2. So my force is going to be what? W times L, the area of a rectangle. Or we can plug in what that's equal to. W is rho g z b L. Or in English units, it would be gamma z b L. Here's your pressure. This is basically the area it acts over. There's your pressure. This is the area it acts over. I find most students to find this equation completely mind-boggling. And it's because they can't remember, well, what's rho and what's B and what's L and what's Z. So I really do want to encourage you to go all the way back to your pressure equation. Start there, find the pressure. Then think, okay, well, to get it to a distributed load, you're multiplying it by how deep into the page does it go, that B dimension. And then finally, you're taking the area under that distributed load curve to replace it with a force F. We did the horizontal plate. Let's do a vertical one. So what if we have a vertical plate or surface? So picture looks like there's my vertical surface. I have a surface of the water up here. So I want to look at maybe this left edge over here, this left surface right there. First of all, we know that the pressure is going to be different at the top where it's shallow compared to the bottom where it's deep. And it's going to vary linearly, so make that a straight line. And we are going to need that breadth B at some point, and we're also going to need to know how deep this is. So I'm going to draw it on here as, call it Z at the top, and then this one would be Z to the bottom. So what I want to do is I want to calculate the pressure at the top and bottom, then convert those pressures into distributed loads at the top and bottom, and then use our great distributed load techniques to replace it with an equivalent force. So let's try that. Pressure at the top. Pressure at the top is rho g times z at the top, or pressure at the top is gamma z at the top. Just depends on your units. Let's do pressure at the bottom. P sub B, pressure at the bottom, is rho g z at the bottom, or gamma z at the bottom. We got the pressures. Let's make it 2D and let's do distributed loads. So same idea. We've still got a water surface, but now we're just looking at this a side view two-dimensionally. So we still have a trapezoid. We've got a smaller one at the top, a bigger one at the bottom. There is our distributed loading. And we want to find W at the top and W at the bottom. Do you remember how we did this before? Distributed load is just pressure times this breadth, this distance into the page, which I labeled B. So for the distributed load at the top, it's just pressure at the top times B. And distributed load at the bottom, well, that's just pressure at the bottom times B. Finally, let's see how we get to force from here. I have my shape, and my distributed load is broken up into it's a trapezoid, but I'm going to break it up into a rectangle and a triangle. The force for the rectangle, just the area of a rectangle. Well, how tall is the rectangle up here? It's just W at the top. And how long is the rectangle right here? That's the depth. Well, wait, we actually can calculate that. We know that the top was Z below the top, and this is Z bottom. If I just subtract those two, I will have this dimension. So I'm going to multiply this by Z bottom minus Z top. I'm assuming that Z gets bigger as you go deeper, because that's usually how we do submerged things, is we have the depth underneath the surface as being big and positive when you go deep. So there's the force from the rectangle. Where is it going to act? Exactly halfway down. Let's do the force in the triangle next. Well, it's a triangle, so you're going to have 1/2. And one of the sides of the triangle is the same height that I just had, the Z bottom minus Z top. And the other side of the triangle is this one right here. Well, I don't know how big that is, but I knew that this height up here was WT, this was WB. I just need to subtract them to get the height of the bottom of the triangle. So what I need here is WB minus WT. And I'm just doing this all symbolically for now. This is a reminder to you that we used to do trapezoids by breaking them into rectangles and triangles. And then you can find those two forces. The rectangular force acts halfway down. The triangular force acts a little bit lower, because remember, the centroid of a triangle is 1/3 of the way up from the bottom of it. So for most problems, you're perfectly fine just getting into a rectangular and triangular force and knowing where those act. You don't necessarily need to combine them. If the problem wanted you to find the total force, you could sum them. If you need to find the actual location of the result, you'd need to do a moment balance to find out the location of that total force when you're done. Last thing I want to do, we did flat horizontal plates. We did vertical plates. The other thing we really need to do are curved or angled surfaces. And they can be hard, but they're not actually that hard. I'm going to show you the easy way to do them. Pressure on an angled or curved surface. Let's say we had a dam here that's made up of like a parabola. And so the water is sitting over here on this side. And we are interested in what the water's doing to this dam that I just drew. Now remember what pressure does. Right here at the surface, we're going to treat the pressure as being 0. And then as you get deeper, it's going to get bigger. But it's also got to always be perpendicular to my surface. So can you see how this is going to get kind of complicated? I'm going to end up with this really complicated pressure that's getting bigger as I go down and changing direction. So if you wanted to try to sum the forces, it is going to be a lot of work and some calculus as well, because we've got to account for the fact that it's changing in magnitude as well as changing in direction. So the way I solve curved surface problems is I do not analyze the pressure like this. Instead, I want to analyze and find the horizontal force in one step, then the vertical force in another step. I'm going to draw it kind of like this. There is my dam, and my water is coming into the top of it, and I'm actually going to cut through the water. Think about cutting through the water right there. And what I want to do is analyze the pressure on that cut open face of water, because that is going to be all of the horizontal load right there. It turns out that the horizontal components of all of these complicated things are actually just equal to this over here. If you just take a vertical projection off to the left, get the pressure on that, that is the net horizontal force that also acts over here on this curved surface. So that'll take care of the horizontal piece. In this case, it looks like it's just a triangular distributed load. So I'm simply going to replace it with an overall net horizontal force, FH. Now, what about the vertical force? It turns out that's also pretty easy. Think about all of this water in here. What that water is actually doing, it's got basically no pressure acting on the top of it, but the water itself is very, very heavy. And so the way we can calculate the vertical force is to find the weight of all the water that I just shaded in. That is what is pushing down on my dam. So the weight of the water inside that area. How are we going to do that? We're going to find the weight of the water it's going to be equal to rho g times the volume of the water, or gamma times the volume. So it's either density times g, that gets you force per volume times volume, or specific weight, which is weight per volume times volume. How are we going to get the volume in that blue shaded area? It's going to be the area times our friend b. That is that breadth into the page. This one that I drew kind of looks like a parabola. There is a formula for the area of a parabola in the back of our textbook. You could integrate as well if you really wanted to. So that is the easy way to find the pressure on an angled or curved surface, and that's how I want you to solve those. Let's do 2 quick examples to practice this. So first we have this big tank. I think it looks like a fish tank, although it's 3 meters by 2 meters. It is a giant fish tank, so maybe one at your local aquarium or something. And we're told the tank is filled with water to a depth of 4 meters. And we were supposed to find the resultant force that the water exerts on one of the ends, A, and one of the sides, B. And then we're going to safely remove and save our fish and replace the water with oil. And the oil is going to have a different density than water. And the question is, how deep would we need to fill it up with oil so that it provides the exact same force on the sides? Solve this in 2 parts. First, we're going to solve the water problem. Then we'll go solve the oil problem. We want to do side A. So what does side A look like? Kind of trying to draw this in perspective this way. The idea is that we're going to have a pressure that starts at 0 at the top, and it's going to end up being an outward pressure at the bottom. And it's going to vary kind of linearly like so. You can see 3D is not the best way to draw this. So we are very quickly going to switch to 2D, if that's all right with you guys. So 2D is going to look like this. It's just a triangular distributed load because we're just calculating the pressure from the water on down to the bottom. Well, let's figure out that pressure at the bottom. It's going to be rho GZ or gamma Z. What units are we dealing with? We're dealing with SI units, kilograms per cubic meter. So we're going to do rho GZ. Let's plug in some numbers. The density of water is 1,000 kilograms per cubic meter. G is 9.81 meters per second squared. And Z is the depth, which we're told is 4 meters. So the pressure at the bottom comes out to be 39,240 newtons per square meter. I want to convert that in 2D into a distributed load at the bottom. Well, that's just pressure at the bottom times B. All right, that's 39,240 newtons per square meter. And B is the depth. It's how far into the page are we going? This is B right here. Draw it on the picture. Well, looking up at the picture, since I tried to draw this with the same perspective, that means B for side A is 2 meters. So multiply this one by 2 meters, and I get 78,480. Now it's newtons per meter if you're keeping track of your units. So we went from pressure to distributed load. So finally, the resultant force on side A is a triangle. So it's going to be 1/2 the base, which is our distributed loading that we just found, times this other side, which is D. So 1/2, 78,480 newtons per meter times the 4 meter depth. And that comes out to be 157,000 newtons or 157 kilonewtons. Let's try side B. Should be pretty similar. It's okay with you guys. I'm just going to jump straight to the 2-dimensional picture. Okay, can you see that the pressure at the bottom is going to be the same, 39,240 newtons per square meter? The reason is same fluid, same G, same depth, same pressure at the bottom. Next step, we need to find the distributed loading at the bottom. That is going to be different. It's pressure at the bottom times B. So it's still our 39,240 newtons per square meter pressure, but then B is different because our side B here extends for 3 meters, right? We're looking at it kind of from the side over here. We got a pressure pushing outward this way, and our B is how far back into the page it would go once we turn that and look at it on its side. So we're multiplying by 3 meters this time, and that gives us a bigger number, 117,720 newtons per meter. And so finally, the resultant force on side B is going to be, it's still a triangle, so it's 1/2. One of the sides is 117,720 newtons per meter, and then the depth it acts over is 4 meters. Meters cancel, and we end up with 235 kilonewtons. And I think it should make sense that because side B is longer, it's going to have a bigger force acting on it than the shorter side A. Let's do oil. We can either do side A or side B. We just need to compare the two. So I decided to do oil on side A. We need to do the whole calculation with oil. If you want to draw a picture, you can. This time we do not know the depth D. That's what we're trying to solve for. First, we need to find the pressure at the bottom for the oil. Pressure at the bottom is going to be rho GZ. Well, rho is now the density of oil, not water. So we're going to do the 900 kilograms per cubic meter. G is still 9.81 meters per second squared. And then Z, that's the depth, is now our unknown D we need to solve for. Let's get the distributed load at the bottom. It's pressure at the bottom times B. We're doing side A, so B is 2 meters. So this is going to be 900 kilograms per cubic meter, 9.81 meters per second squared, times D times 2 meters. Now we need to get the force. The force on the oil on side A. Well, that's going to be the area under that distributed load triangle. So that's 1/2. One of the sides is W at the bottom. The other side is D. So the 1/2, because it's a triangle, times 900 kilograms per cubic meter times 9.81 meters per second squared times my 2 meters. And then I've got a D squared because I had a D right here and I just included another D right there. All right. And we know that that needs to be equal to the force from the water at A, which we found what was the force at A from the water. 157,000 newtons is equal to that stuff. Solving for D, D comes out to be 4.22 meters. And it should make sense that D is a little bit bigger. Since the oil has a lower density than water, that's why oil tends to float on top of water because it's got a lower density. You're going to need more oil to get the same amount of force on the side of the tank. Let's do one more example. It's going to involve English units and a curved surface. So lots of fun. So we have this dam here, and we're told that it's a parabola, y equals 0.25x squared. We're given some dimensions here, 10 feet over, 25 feet up. And we're told that it is 30 feet long, and that's the dimension into the page. And it's English units, so we're given specific weight. And we are supposed to find the resultant horizontal and vertical force components that water exerts on the dam. Let's do this in 2 parts. Let's do the horizontal separate from the vertical because I don't want to deal with the curved surface. And so doing that, we've got the dam right here and the water right there. And I'm actually going to cut the water open along a vertical plane, because that allows me to just replace that with a nice distributed loading triangle. So I need to find the pressure at the bottom. That's going to be gamma Z this time, no rho G's because we're not dealing with SI units. Well, gamma is 62.4 pounds per cubic foot. And the depth at the bottom was 25 feet. And multiplying that out, I get 1,560 pounds per square foot pressure units. Next, I already drew this 2-dimensionally, but I need to get that distributed loading at the bottom. Well, that's pressure at the bottom times B. So that's going to be 1,560 pounds per square foot. And I need to multiply it by how long this goes into the page, which is my 30 feet. Cancel the feet, and you end up getting a distributed load of 46,800 pounds per foot. So those are good distributed load units. It's a force over length. So to get my total net horizontal force, it's going to be the area under the triangle. Area of a triangle is 1/2 the base times the height. The base would be the 46,800 pounds per foot, and the height would be the 25-foot depth of the water. The feet cancel, and we get 585,000 pounds. That's how you know you've done all the right multiplications, is if your units come out in pounds at the end. If they don't, you might have forgot to multiply by a length somewhere. And if you want, you can call that 585 kips. And if you wanted to know where it acted for some other part of your problem, it acts 1/3 of the way up. So this distance would be 25 over 3 feet. Doing the vertical part. Now we're dealing with the weight of this water. So I need to figure out how much this water weighs, and that will be my vertical force. So the vertical force is the weight of the water above the dam. Well, that's going to be gamma times the volume of water. Well, gamma is 62.4 pounds per cubic foot. And then volume is going to be area times how far it extends into the page. You can integrate this if you want, because we were given a function at the beginning, but I don't want to integrate because I want to find this faster. And if you look in the back of our textbook, you will find that for a parabola that has sides of A and B here, the area is 2/3 AB. You can also find out exactly where the centroid is located if you needed to know where this weight's effectively going to act. And in this case, that distance right there is 3/8 B. But the area on the inside of a parabola is 2/3 AB. The area on the outside of the parabola would be the other 1/3 of AB. So we're going to use that. It's the inside of the parabola here. So we're going to do times 2/3. What are our A and B? I think they actually gave those in the original picture, right? Here's our parabola. One side is 10 feet. The other side is 25 feet. So 2/3 times 10 feet times 25 feet. That's the area, but I need volume. So I need to multiply it by how far into the page it extends. That's my 30 feet. So that'll give me volume. And when you multiply this out, you get 312,000 pounds or 312 kips.